Thank you everyone for joining us. We're here today to discuss federated learning, AI, and data security together with Security's very own David Hochhauser. And we're also joined by a number of AI and data security experts, including Abdul, Rahman, Sattar, Mikhail, Yurochkin, Daniel, Zakrisson, and Tushar, Kant. We're going to start our webinar today with a brief introduction from David Hochhauser on today's discussion topics, and then our panelists will each get a chance to briefly introduce themselves. Afterwards, we'll get into a bit of a deeper discussion on everything related to federated learning, AI, and data security, including its ongoing threats and solutions. As usual, we'll leave about 30 minutes at the end of our discussion for a short Q&A. So if you have any questions throughout, feel free to drop them in the Q&A section below, and we'll get to them later on. Now, we have an impressive lineup of panelists here with us tonight, so I'm excited to have them introduce themselves to you. But first, we'll begin with a few words from David before we hand off the mic for introductions. David, take it away.
Hey, thanks a lot, Shterny. And as you said, so I'm Dave Hochhauser. I'm Chief Revenue Officer for Hub Security. And Hub Security is essentially an extremely sharp group of hardware and software engineers, and we're focused on cybersecurity, and we'll see why that is such a strong interest and impacts AI in a few minutes. So first of all, I think we have an absolutely really fascinating discussion today and a phenomenal group of experts. I'm actually looking very much forward to, while contributing somewhat, also really looking forward to learning a lot as well during the discussion. So just 2 minutes, why we're holding this session and what the general focus is of the session. So why so much, why about federated AI and security from that perspective? So one, if you're reading in the journals, you'll see a lot of stuff going on with AI. And in healthcare, there's just really kind of an explosion of the effort, everything from diagnosing diseases through monitoring equipment, and figuring out what the treatments are. So it's a fascinating area, but as in everything in healthcare, there's also an enormous issue dealing with the protection of the data and data privacy. So they kind of have to balance each other out. We have to deal with that challenges. So a lot of the issue here is about federated AI, but also how do we deal and balance some of the security. And federated AI is really one of those approaches that really helps quite a bit with some of the security issues and the data privacy issues at the same time. So let me just give you an example, just for clarity. So I've recently, learned more about a pilot that's going on actually between Intel, University of Pennsylvania, and several other major medical institutions. And they're actually looking at how to improve brain imaging. So when you look at, for example, if you have brain tumors, how do you more rapidly diagnose them and more accurately diagnose them? The thing is, it becomes more realistic and effective the more data you have. It's just a general rule of AI, the more data you have, the more effective it's going to become. The challenge is dealing with the privacy of the information. So they're using federated AI to actually reach out to the various groups to broaden the pool of information that's available to be able to do this analysis. And what we'll see here, as in most of these approaches that you do that, there are absolutely tremendous advantages, but there are also some cons, and there's also a lot of still remaining issues dealing with the security challenges. So today, what we'll focus on is looking at both federated AI in general, what it is, what are some of the advantages and disadvantages of federated AI, looking at some specific use cases, because I think the examples tell an enormous story in and of itself. And then we'll also focus on the data protection and the privacy. One, how federated AI helps, but also maybe some of the gaps and some of the options and stuff to enhance it and complement it, and maybe some of the alternatives as well that are in there. So again, I think there's a phenomenal group of people on this call. So there'll be a series of questions for each of them. Will contribute. And then we'll also, it's certainly, please type in your questions, because this is a great group to get the answers from. So I truly hope you enjoy this. And back to you, Shterny, to continue. Thanks a lot.
Great. Thank you so much, David. It was a really great introduction. And I'm glad that you could join us today, too. I really like it, what Tushar mentioned when we did a dry run for this event, how diverse this panel is. So really just soak it in. David's, tuning in from New York. I'm tuning in from Jerusalem. Tunar, you're in the West Coast. Tushar, sorry, you're on the West Coast, if I remember correctly.
Yes.
So we get many different perspectives and many different contexts, which is really great. So I'd just like to take a few minutes now, if we could do a quick introduction round, starting with Abdul. Would you mind giving our listeners a bit of background on yourself and your field of expertise?
For sure, Shterny. So, hi everyone. I'm Abdul. I'm the lead architect of cybersecurity analytics at TELUS. So TELUS basically is one of the biggest telcos in Canada. So over here, my team is essentially working on cybersecurity analytics data lake that we are building for securing TELUS and also for our customers, and essentially the AI and machine learning use cases for intrusion and threat detection using big data and AI and machine learning, and also looking into IoT security and connected and autonomous vehicle security. Currently very early in the research phase, but leading academic collaboration on behalf of TELUS with quite a few institutions within Canada on that. So outside of TELUS, I'm also a steering committee member at various AI and machine learning communities. I've also been a speaker at both national and international conferences on big data and applications of big data for cybersecurity analytics at scale. I'm also the Toronto chapter lead and steering committee member of automotive security research group, which is focused on automotive security.
Wow, a long list of accomplishments. Great. Thank you so much, Abdul. I'm glad that you could be here with us today.
Thank you, Shterny.
Yeah, next I'll hand over to Mikhail.
Hello, everyone. Thanks for inviting me to join. I'm a research staff member at IBM Research AI in Cambridge, and also I'm working in collaboration with MIT as part of the MIT IBM Watson AI Lab collaboration. I'm doing research in topics such as federated learning, which is today's topic, but also algorithmic fairness, applications of optimal transport in machine learning, and also Bayesian modeling. My work is often published in ML conferences such as NeurIPS, ICML, ICLR, and others. So I'm really excited to be here and discuss federated learning.
Great, we're excited to have you here as well. Daniel, you're next.
Yes, hello. Thank you for inviting me as well. So my name is Daniel Zakrisson. I'm from Sweden, where I'm I'm the CEO and one of the co-founders of a company called Scaleout, where we are the creators and maintainers of an open source federated learning project called FedN. And we built FedN really to provide a scalable, very flexible and production-ready federated learning solution. And that's not really tied to any specific machine learning algorithms, so we can run it across the different neural network types, Keras, TensorFlow, or PyTorch, but also in we using it with the boosting or bagging models and or basically any kind of model you can dream up. But in the company, so we have this open source project, but also in the company, we are working with partners then. And today it's around 15 different use cases from pharma, medtech to financial services, in air traffic control, and also in the automotive industry around federated learning. So I'll be happy to talk about also many different kinds of use cases and both benefits and challenges in those.
Great, and we're looking forward to digging into some of them with you today also. Tushar, go ahead.
Thank you, Shterny. I'm Tushar Kant. I run a global forum in artificial intelligence for my undergrad alumni IITians across the world, which is 1,500 people coming from almost every top major technology firm as well as academic institutes. In terms of my professional career, I have worked at Amazon Web Services, Facebook, VMware, Intel and Sun in technology industry. And then on the Wall Street side, I've worked for Bank of America and GE Capital. My most recent focus has been on building businesses in artificial intelligence, leveraging cloud computing, which can work across multiple different verticals, be it healthcare, financial services, retail, manufacturing, all of them. And through the forum which I run, we have organized a lot of events to collect the common thought process and intellectual IP of people in terms of developing frameworks, how we can leverage artificial intelligence. Federated learning and security are very important topics. And completely agree with how David introduced this whole panel, that getting more data is important, but you have to make sure how we balance it against security. And that's where federated learning, differential privacy, confidential computing, a lot of these paradigms come into it. Looking forward to learning from this international panel. And thanks for the invitation to join you all. Thank you.
Great, thank you, Tushar. So we kind of split our discussion up into a few topics, and I want to start with the first one, which is about federated AI. And I wanted to start with you, Abdul, and maybe just get your input on this. Kick us off with, what is federated learning, and how does it differ from traditional AI, ML approaches, artificial intelligence, machine learning approaches that exist?
For sure, for sure. I mean, before I go into federated learning, perhaps I'd actually start with some of the other common approaches to machine learning systems, and to then basically contrast it with federated learning. So essentially, the most common approach basically is that both the training, currently, that the training and the inference basically happens on the cloud. So essentially, in this sort of paradigm, the devices would be sending their data basically to a central server, which would likely exist in the cloud, and then on the cloud, the training would happen. The model training would essentially happen, and then during the inference time, basically, the devices would be sending the data to that central server, to the cloud essentially, and the cloud would be applying the model to the data and then returning the result back. So the problem with this sort of approach is the multiple problems. Like one basically could be data privacy. So essentially, there could be data sovereignty issues and data privacy issues. So the end devices might not be able to upload the data, that private data, to the device. The second issue could be that there could be huge volumes of data depending on the use case. So in this day and age, when we are talking about IoT and connected and autonomous vehicles, according to a survey by 2025, IoT devices would have generated around 70 to 80 zettabytes of data. I mean, which is so it's not possible basically to upload this data to a central server to do analytics in the central server paradigm. Also, when we are talking about connected cars, according to a survey, a self-driving car basically can generate around 40 gigabytes of data per 8 hours of driving. So that again, basically, I mean, when you multiply it with the number of vehicles that we have on the road, that again basically grows pretty quick. And again, it's not possible to upload this huge amount of data to a central cloud for analytics. So that's another problem. Then the other problem could be essentially network disruption. So essentially, because the device is depending on a central server for applying machine learning models to the data points, in cases where there's some sort of a network outage between the end device and the cloud server, then the application to the user would be unavailable. And this is not good, basically, in safety critical issues. So these are some of the key problems, basically, with this whole central paradigm. So now the other approach could then be that, okay, let's train the machine learning model on the cloud, but then do inferencing on the device itself. So essentially, once the model is trained on the central cloud, then have the model on the device, where the device would then apply it to the data points from in the inferencing stage. And that does basically go around the data privacy problems and also the big data problems that I mentioned for IoT devices and such. So then I guess the other scenario would essentially be that the training and inferencing basically happens on the device itself. So in that case, the device basically would be training on its own data, and then the model would essentially completely live on the device where it would be used for inferencing. But the problem in that sort of scenario would be that the device is restricted to its own data set, and the device might not have that much amount of data to train robust models. So in a federated learning scenario, we sort of flip the problem on its head, where the devices would essentially be collaboratively training machine learning models without basically like sharing their data with each other. So that basically gets around the privacy issue. So the way it would essentially work is that this collaborative training in a vanilla federated learning setup basically happens with a centralized parameter server. So essentially, at the beginning of time, the parameter server would be pushing down an initial seed model to the end devices, and this initial seed model could either be randomly initialized, or it could be initialized through some sort of seed data that the parameter server might have. The end devices would then be doing local training on their end to further train this model with their local data, and then they would be uploading this locally trained model back to the devices. So at this point, only the model parameters are being uploaded to the central cloud, and the data is still within the device itself. The parameter server would then be aggregating across like all these different models to update its copy, and then it would be pushing its updated copy back to the devices. And this basically goes on in a loop until the model convergence is achieved. So this essentially gets around the data privacy issues. I mean, it basically mitigates some of the data privacy issues, although for stricter privacy, one would need better techniques like differential privacy and confidential computing that Tushar mentioned initially. Also, one thing that I also want to call out with this federated learning is that it democratizes machine learning as well. Essentially, like the small players who don't really have enough data, by collaborating through this federated learning approach, would essentially be able to train machine learning models and would be able to compete with big players who have a lot of data.
Great, thank you. My next question is for Daniel. Where's the line between research and production readiness when it comes to federated learning today?
Yeah, so yeah, that's a good one. So because right now we think about federated learning in a very, very wide context, and we think about it. So basically, we always start with thinking about it as a solution to a data access problem. And we have data in silos, and we really can't access this data to pool it somewhere and train centralized machine learning model on it. Okay, but then if we take that big problem and break it down, there are some scenarios that are quite straightforward, where federated learning is not really, it's not rocket science. You take these models and like Rahman now explained, you just take weights from individual models and put them together. So there is one algorithm called federated averaging. It's quite well understood. It's quite easy to implement. And as long as you have a machine learning model that's based on weights, you can just take all of these weights and weigh them together. As an example, the way that we have implemented this is also through a hierarchical approach. So we have like several different aggregators in the middle layer. So that way you can also reach scalability. So I would say that like models built or federated learning built on neural networks or other models that have easily accessible weights, that where it makes sense to weigh these together or average these weights together. That's really production ready today. But in federated learning, we also typically divide the cases based on how we split data between different clients or different nodes in the system. So in a system where you have like the same feature, but have several different participants or several different data sets with the same features, we call it horizontal learning. And this is also quite an easy use case to implement and run. But if the data is split so that you have sort of the same samples or IDs to samples, but the features are split across many different participants. So for instance, you have a bank and an insurance company, so they have different data points for the same people, and they would like to collaborate and build maybe a fraud detection model, for instance, or a money laundering detection model. This problem becomes much harder, and there are really no solutions in place today that I would say are production ready for the vertical case here. So if we sort of generalize this a little bit, we can say that, okay, so horizontal federated learning, where the data is split across many different, or the samples are split between different data sets, that's good to go. If you go into other algorithms that are not neural networks, or like, then it's not as easy to say that we have something that is production ready. It's more research. And also we have these vertical cases that are maybe the most interesting, I would say, from a use case perspective, because that's really where we enable this collaboration between different parties. We might have like private data, and you might even think about sort of the extension of not only collaborating with other parties, but also maybe collaborating with competitors, that you have a common problem where you still have a joint like interest in solving this problem. Maybe collaboration is best for both of you, even if you're fierce competitors. But we're not really there yet to put that kind of solutions into production.
Thank you. I want to circle back to Abdul for a second. Maybe you can expand a bit more on what are some of the different architecture and topologies when it comes to federated learning. And maybe after this, we'll get into a bit of the challenges behind it.
For sure, Shterny. So before I start with that question, I think I lost my train of thought when I was talking about various other cloud paradigms for federated learning, and I think I mentioned that the training basically could happen on the cloud, and the inferencing basically would happen on the device. And I lost my train of thought as to what the disadvantages over there would be. So essentially, the disadvantages over there would be that the data would still, because the training is still happening on the device, on the cloud, the device would essentially have to be, the data would have to be uploaded to the cloud, and there would still be privacy issues, and also the data volume over there would be a concern, right? So just wanted to sort of fill that in. So coming back to the question itself, where what are the different topologies? So essentially, there are a few different ways that we can classify the federated learning system architecture. One is basically like one of them could essentially be on how the data is distributed. So if we basically take that into account, then federated learning could be divided into horizontal federated learning and vertical federated learning. So I think Daniel already touched on some of that. So horizontal federated learning basically is the vanilla setup that I mentioned, where these various devices would essentially have non-overlapping data points, but they would essentially be tracking the same features for the data points. And in this case, the training would essentially be similar to the vanilla setup that I mentioned. Through the parameter server, the devices would essentially be collaborating to train their local machine learning models. Then there's also a vertical federated learning, and in vertical federated learning, basically the devices have overlapping data points, but they would be tracking different features for those data points. So essentially, like, think of them as various different verticals that share the same customers, but now they're tracking different features for those customers. So in that sort of setting, these different business entities would be collaborating with each other and sort of pooling their data to train their local machine learning models. But now the business entity has access to not just its features, but also to the features that its peer is collecting basically on those data points. So essentially, the models would be more richer because there are more features, and it would essentially result in models with better predictive power. So then the other way basically of classifying federated learning is based on how the orchestration happens for the whole learning process. So in that case, the vanilla setup that I mentioned for federated learning is basically like centralized, centrally orchestrated through a parameter server, where the parameter server basically like selects the initial federation, and then it would essentially orchestrate this whole learning process through the federation. But then the problem with the centrally orchestrated architecture is that it's a single point of failure. So if the parameter server is compromised or it fails, then the whole learning process can fall apart. And that's where there's been quite a bit of research and work in peer-to-peer federated learning, where rather than having like a single parameter server for doing model aggregation, this whole model aggregation would happen in a P2P, in a peer-to-peer fashion. And the aggregation over here could happen in a few different ways. A peer basically could be training its local models, and then for aggregation, it could select like a few peers at random, and then broadcasting its model parameters to those peers, and those peers would then be doing the aggregation. Or it could essentially be happening in a more orderly fashion, where you sort of like where the updates basically go around in a circle or something like that, right? In peer-to-peer, I also basically want to call out blockchain architectures for federated learning. So in this case, blockchain basically would be used for orchestrating the whole federated learning process. So essentially, the blockchain would be selecting the initial federation in this case, and the clients or the trainers basically would be uploading their parameters to the blockchain, where the miners in the blockchain would be looking at those updates, and they would be mining them, and those epoch updates basically would be stored in a blockchain basically. And at the end of this whole federated learning process, even the final model could be stored in the blockchain. So essentially, like some of the advantage that it has is, again, there's no centralization and no single point of failure. But some of the other advantages that it also brings is this whole incentive and reward mechanism, where the clients would be incentivized basically to participate in this blockchain, in this federated learning process, because as we know, blockchain could be translated to some sort of like monetary reward as well. But other than that, I think like a great other advantage basically is that you can even have like the model, because the final model lives in the blockchain. External buyers can basically like come and buy that model, and this could essentially set up a whole reputation system for the clients that are participating in the blockchain, and basically like model as a service on the blockchain itself.
Great, thank you. I'm going to get to Mikhail and Tushar. Actually, I have a question for you, Daniel, next, but I see you want to jump in. Did you want to add?
Yeah, I can just add a small comment on that, because we actually implemented a decentralized federated learning solution on Ethereum, so one of the blockchains that are available. And just one comment from that implementation was that, or an observation was that when we're trying to scale that up in the solution and the tools that we were using, and we were storing all the data also using decentralized storage solutions. So this was IPFS. But the main limiting factor for us in those tests were actually the storage of data. So we could see that this system that we had, they totally break down around when you have 20 clients or so, because these storage systems cannot handle and propagate data. So that is generated, and the models also that are generated in the update process. So it just completely grinds down to a halt. But it is a really, really interesting area. But I also put that sort of in the research bucket for now. But it would, yeah.
You can tell us a bit about or describe a bit for us the core challenges that exist when it comes to federated learning from your perspective.
Yeah. So yeah, it actually touches back. So when we have been building systems that are a little bit bigger now, we generally tend to think or see that there are three main core challenges. So the first one is about scalability, that because you have many different clients involved, and that generates many models, and you have this aggregation process that will end up taking a lot of time, and in most cases, most of the time is actually spent uploading and downloading models in the system. So like scalability is a really, really important like core challenge to reach these like kind of big systems that we're aiming for when we want to have like hundreds of thousands of cars doing federated learning at the same time. The other core challenge is also like an engineering challenge, I would say, and that's built around system heterogeneity, that when you have these systems, they're out in a network, they all have different connections. So sometimes they lose connections, sometimes they're busy doing something else. Someone lags, someone joins in, someone like, or maybe joins in the wrong epoch. So like taking care of like just managing this sort of very, very complex system of peers, that's also really a main challenge when you go from like controlled setups to real distributed setups. And the third one is about data and the data heterogeneity, because like one of the key starting points here is that we don't have full control over data. We don't know what data is on each device. So this data, it can be faulty, it can be very, very unbalanced, so that like the model generated on one device might differ very much from another device, or one model might not see all the classes that we want to train it for. That is like key challenge, and the way to deal with it is to really think about validation of models. So when we train a model, how do we validate that this model is good? So I would say that's like top three challenges, and then you can go on and have like other challenges, because so security is an important one, and we can talk more about that. But I think that security and data privacy is also related, and that is much more important in certain use cases. So for instance, when you're collaborating with others or where data is very sensitive. But in the case of like a smart light bulb, data privacy is not that important. It's more about these other challenges that comes first.
Great, thank you. Mikhail, I wanted to ask you, what is model fusion and how does it impact federated learning?
Thanks for asking. Yeah, so model fusion is a kind of a, I could say, a special case of federated learning. In particular, it's a setting where, in the most extreme sense, we only allow to exchange the information between the clients and the server once. So I think Daniel and Abdul mentioned how, like in a usual federated learning setting, the initial model is propagated to clients, and then they start kind of exchanging their weights and so on. However, maybe the clients have already trained some models and they already have some models. They still want to collaborate, but they only have, they have their local models. They don't want to start training from scratch. So we want to combine those models. And in addition, it is possible that they might not have the data that they've trained their models on, for example, because the data needed to be deleted or something else like that. So for instance, some of the regulations, they prohibit prolonged data storage. So the model might be there, but not the data. So in this case, all we have is the model parameters, and we need to combine them from different clients. So, and how to do that? Well, we cannot just simply average the model parameters because those models were trained independently. Indeed, averaging neural networks is a kind of, parameters of neural networks element-wise is not a very good idea, because if you were to train a neural network, the simplest one, on the same data twice independently and then average, that would be garbage out. And the reason for that is sort of, if you imagine this, the diagram of a neural network in your head, like imagine it in a physical world. So you have this hidden layer, and there is like these balls, which are the hidden neurons. And there are sort of strings connecting those balls to the inputs and to the outputs, right? But there is no prescribed ordering between the neurons of the hidden layer. So you can easily imagine in a physical world, you could kind of move them around along with the strings attached to the inputs and the outputs, and the neural network is not going to change. So this means I can, take a neural network, reorder the neurons, so which changes the ordering of the weights in the matrices, and it will be the same neural network. However, element-wise averaging of something like that does not make any sense. So that's why we need something more, clever algorithms than simply just element-wise averaging that's prescribed by the federated averaging. And yeah, so model fusion kind of, at least the techniques we've been developing in our group, So it tries to figure this problem out. So in particular, we try to establish some correspondences between neurons of different, you kind of, like dissect the neural network, like get all of its inner parts out and try to look at them and like, okay, this neuron of this neural network corresponds to this neuron of the other neural network. So they should be averaged. So the models, like the approaches we developed, they try to figure out that part. And in addition, so what's interesting, I think Daniel mentioned how some clients might not see certain classes, right? So it's a problem of data heterogeneity. So in particular, the different clients have different data distributions. So what we want to do is that we want to also allow the global model to be bigger in size than the local models by saying, okay, this neuron of this client, it's just, does some function that no other client have learned. So it should be, kept separate.
Super fascinating. Thank you. And Abdul, I wanted to ask you, how does federated learning compare to split learning?
For sure. Yeah. So, I mean, before I go into split learning, I guess like I'll mention some of the problems that it sort of tries to solve, or it solves like that happen in federated learning. So essentially, in federated learning, depending on the model could be huge. So that essentially would take up a lot of like compute cycles on the client, and then also if the model is pretty big, then it might also be a lot of like communication bandwidth for the client as well. So those are some of the problems which I think like split learning basically solves. It was a parallel technique that I think was sort of like started in MIT. So what they sort of found was that through split learning, the resource footprint was pretty small in terms of both compute and network usage, and also it basically converged much quicker than federated learning approaches. So the way the vanilla split learning architecture basically is that if I step back a bit, so in federated learning, the model basically is replicated, the same model, the entire model is replicated across all the different clients and trainers, and they basically train the local version of their model through a parameter server in a vanilla federated learning setup. In split learning, what happens is that the client basically just has a portion of the model. So the model basically is like sliced, and the client basically would have only a small portion of the model, and the rest of the model basically lives within a server. So essentially, in forward propagation, from the inputs to the activation layer basically would happen, the forward propagation would happen on the client, and from the activation layer onwards, those activations are essentially transferred to a server where the rest of the forward propagation basically happens, and then the backward propagation flows from the server down to the client, and essentially, and in this way, basically, the federated learning, the split learning model is trained like across the client and the server, and then I think besides this vanilla setup, there are a lot of other setups that are possible as well, where multiple clients basically might have like non-overlapping features for the same data points, and they might want to train the split learning model in a collaborative fashion. Also, there's a split federated learning, where split learning basically is combined with federated learning to train models in models basically across clients. Other than that, so there are multiple architectures possible over here with split learning. One thing I also want to mention is how split learning achieves privacy, because it's possible that an attacker that's basically looking at the activations from the client might be able to sort of infer what the data points are in that client just by looking at the activations. So that's where in split learning, what it does is that you add a distance correlation function between the distance correlation measure between the inputs and the activations to your loss function. And what it does is that it actually minimizes the distance correlation between those activation and the input layer. And so what that means is that given the activations, you wouldn't be able to sort of like figure out like what the inputs are. So you can go from inputs to your activations, but looking at the activations, you wouldn't be able to figure out like what those inputs are.
Great, thank you. What a great definition. Mikhail, I would like to ask you, what are the gaps between federated learning in practice and in research, and how can they be mitigated?
That's a great question. So I mean, I think it's a question sort of for everyone in a way, because I'm more working on the research side. So I develop algorithms for, addressing some federated learning challenges that, we as researchers oftentimes believe are important. So, but maybe in practice, some of these challenges are more relevant than others. Maybe there are some other challenges that researchers do not see. And I think the other important part is the data that we use. So the original federated learning papers, maybe 2017 through 2018 or even 2019, they mostly used just something really naive. They took the standard machine learning data sets, such as the MNIST handwritten digit classification, and they started splitting them into chunks in all possible ways. So everything had their own way to do it. And then they were just, pretending those as a client data sets and training models on them. I mean, which is a fine kind of first attempt, but I think real federated learning is not quite like that. And then, I mean, there have been some effort on the data set side. So there were better data sets proposed too. There is this set of sort of federated learning benchmark data sets. One of them is this, people call it federated MNIST, which is roughly the collection of, like letters and numbers that were handwritten by different people. So here's the people as the clients, and then everybody might have their own handwriting style. They might have a different distribution over letters and numbers and so on. So I think this is closer to reality, but again, I think in real federated learning, maybe it's still not representative enough.
And what are some other exciting challenges and innovations that are happening right now in federated learning research? Yeah,
so I mean, they've been kind of going through years. So people have been looking at problems such as Byzantine robustness. So what if some client kind of is malicious and tries to send, or maybe they just something broke locally for them and they send some garbage instead of, weights or something reasonable that we expect from them. So this is one setting. Another one is fairness. So it is easy to sort of, without additional precautions, it's easy to train models which favor the clients with more data and more data diversity, rather than clients which sort of represent some corner of the overall training distribution. So those might, they might not even benefit from federated learning. It's also not always verified even in papers that every client truly benefited from federated learning. Oftentimes we look at some, global model performance and some data, but what about the local data sets? Did we actually help everyone? And this is important. I think we should make sure that everybody, at the very least, got some benefit out of this, and ideally, like the clients which have fewer data points or have some like hard examples, they should also benefit. And the other part that also kind of follows up on that is personalization. So it's a pretty exciting topic. So I think it's kind of really picking up in the last year. So I remember being interested in this topic like a year and a half ago, and there were almost no academic works on the topic. And then in the last year, there is a lot. And yeah, so the interesting part, it turns out that just doing the simplest thing one could ever imagine, which is doing federated averaging and then fine-tuning the model for every client locally on their data, is actually a principal way to do so. The reason it's principled is because it imitates this idea from meta-learning, maybe for the listeners familiar, model agnostic meta-learning procedure. So it turns out that it's doing something like that, which is actually good for generalization and so on. But it's still, from the research perspective, it's kind of bothering that the most naive approach is just so good. So you always want to do better because the naive approach is boring. So I think that's a pretty exciting. And there are people doing all sorts of things. There is pretty exciting stuff. I've seen someone's paper on, like now every client can have their completely different model, completely different architecture, and then different input features. And the way they propagate information is through this idea of model distillation, or kind of teacher-student learning. So this way, like the global model just passes some predictions, and then they distill those predictions into their local model. So pretty flexible, pretty neat. I think that's interesting things from recent days.
An hour into the discussion, I want to leave time for Q&A, and I don't want to, to be stressed on time. So we're going to jump to the next topic, which is some use cases. And Tushar, I wanted to ask you, what are some typical B2C business to consumer use cases when it comes to federated learning?
Absolutely. And let me give you an idea of a very typical case in business to consumer, which is very well can be transferred to B2B, and I'll talk about that as well. So, good part of federated learning research, for example, started in Google, where they basically wanted to have a way in which they can capture the activities of individual users on Android mobile phones and use that to basically train, let's say, a language prediction model in a centralized environment. Now, how would you do that? So instead of, users may not be comfortable sending their personalized information, of course, from their mobile devices where they're typing stuff to Google. So that's where they started with this concept of federated learning, where the models will be shipped, as Abdul, Daniel, and Mikhail explained, to the end point devices. They will train it with the data that they have. All of it will be sent back to the Google itself, to the centralized server. The next question which basically came in was, hey, what if when when the model parameters are being sent to the centralized server, what if they figure out a way to reverse engineer the data itself? And that's where a concept of secure aggregation came in. So the model parameters, when they are being sent to the centralized server, are actually encrypted. And when they do the model averaging, they do the model averaging on encrypted data, and then they decrypt it. So now the average data is the only decrypted data which Google sees, and everything, or other companies see, and everything else is actually encrypted. The good news is this technology or technique is very applicable to, let's say, healthcare use case. Right now, the whole world is still going through the health crisis. People are trying to figure out, do research, and in future also figure out how to basically develop new and innovative solutions, let's say for new variants of COVID or other kind of diseases. Now, there's a huge amount of data that different hospitals, government agencies, medical centers have. And they're not comfortable sending PII information to a centralized server. And that's where, again, something like federated learning can be very well used, where you basically encrypt the data, and not just keep the data, but encrypt the model parameters, send it to a centralized server. So areas like healthcare can get revolutionized, and artificial intelligence reach and impact on real life of people can be really huge through federated learning. That is from healthcare perspective, which can be very transformational in nature. Financial services companies can also use it, and there can be a couple of other use cases. But the whole concept of letting the user or an organization or an entity maintain the privacy of the security of the data that they have, while letting a centralized server actually leverage it to solve a much bigger business use case is very important. Another thing which I want to also introduce here is differential privacy. One of the key factors people is, hey, when we're sending these model parameters, what happens if there's leakage of that, or the encryption does not work? You can bring in a concept of differential privacy where you still send the same data, but you add some noise to it. So the fundamental characteristic of the data does not change. The fundamental characteristic of the model parameters does not change. You can still capture it at the aggregate level, but the particular data that was in the original form is not sent. So that is basically, you bring in federated learning with what is called secure aggregation. You bring in differential privacy. And the final thing is, which companies like Google, for example, are working, if I'm correct, with AMD, Microsoft is working with Intel, is secure computing. So even when you are actually running the model on the centralized server, what you do it is you do it in a secure environment. What does that mean? So when you're running it on a processor, let's say an Intel processor, an AMD processor, an ARM architecture, you actually have what are called trusted execution environments or security enclaves on hardware, where you basically run these models in a secure environment. And when you do it there, you can maintain what is called data in use security. The concept of data in use security being applied to centralized federated learning training in a decentralized environment becomes very relevant. So essentially, what is happening is the B2C has done it. We are moving into areas like healthcare. You bring in federated learning, secure aggregation, differential privacy, and secure computing together. And that's like a holy grail of what we can do to kind of transform industries. Happy to, have, if you have any clarifications, happy to answer them in detail, Shterny.
Yeah, I'm also interested to hear, what are some of the healthcare use cases for federated learning?
Absolutely. So I would like to, just keep it to 2 or 3. Number one, right now, medical organizations across the world in developing countries as well as developed countries are seeing a huge amount of data from the patients related to their medical conditions. Now, every part of the world, for example, is not equipped to do state-of-art research like the way, let's say, MIT does, or some top companies in Western worlds are doing. They can work with agencies across the world without having those data sift or sent to US directly, and they can basically use it to do research where the research is much more unbiased. Like if you're just looking at data and training models with data in US, for example, with certain number of agencies, your data will have demographics, which is very particular. It may not be applicable to, let's say, demographics in Africa. So you can basically do much more wider, unbiased research and development leveraging federated learning. First thing. Second, privacy rules. Europe has got very strict privacy rules, as we all know. They're not very comfortable, companies there sending data over to US. GDPR and other factors are coming into play. Well, those privacy rules will not become an hindrance in doing international research, because there are a lot of a really solid research institutions. For example, Max Planck set of institutes in Germany, Oxford in UK. We have some reputed institutes in France. They can work with the MITs and Harvards of the world here. So one was getting data from different parts of the world, and now I'm talking about cross-organizational research in healthcare across continents, where these organizations are not basically sending data, but sending model parameters, leveraging federated learning, and using privacy. That is the second thing which is very critical and important. And the third is, a lot of us who are basically working with our systems and stuff like that, we would like to have some kind of alerts which can happen or can give me some hints about, hey, where can I get into my own medical challenges and problems? And we will not like to share our personal data with companies, or with let's say, with companies as well, to give us what are called targeted recommendations, but would be much more comfortable, for example, where lightweight models can be even run at the end consumer devices to monitor certain things for updating models, and doing it with a centralized model to give me some alerts if things are happening. So there are three main use cases. Number one, use of data at an international level across the world for training much less biased models. Collaboration between international organizations for state-of-art research. And third, helping consumers deal with their personal health issues while respecting the security in a federated environment. The two or three very key issues. The last thing I would say is, fortunately or unfortunately, COVID has made a huge amount of data available right now. It's like a mine. This kind of a technology can really help unlock value out of this data. I'm not talking about revenue and growth of enterprises. I'm talking about unlocking the value from perspective of developing new research, new drugs, which can basically change the paradigm and actually save lives, right? I mean, with all due respect to companies like Google and Facebook, this is not about leveraging federated learning to get a $100 billion bump up in revenue. This is about actually saving lives of people on the ground. And I certainly want to put an emotional note here, and I know people are coming from different parts of the world, but the country I'm coming from, which is India, the country is on fire, literally. There are a dozen people in my first family, in my own family, who are down with COVID or have just recovered. There's not a single family which I know people where have not died. I'm not talking about people who do not have access to healthcare. Middle class and upper middle class people are literally dying. I have 1 week back, I have myself started a forum which has got 800 people now, which is like a task force between US and India to help people. And this is I will give you a very specific example. We are trying to figure out how to develop oxygen concentrators which can be deployed in rural areas in India, which has got its own parameters and challenges in terms of low power. How do we collaborate to do a quick research? I know some IITs in India are doing some research, people in US are doing some research, but there are enough regulations which prevents sending data from India to US right now to leverage research work here. Something like federated learning right now can actually save not not tens of thousands or hundreds of thousands, millions of lives in rural part of India, where people are either otherwise just going to die in next few months to come. So you guys understand the gravity of the situation where you're coming from.
Yeah, I think we all have India in our minds right now, and we're all praying for the best.
Thank you.
Yeah, definitely a lot of it, a lot of the impact right now can be mitigated by having proper oxygen supplies. Yeah. And then this is also a matter of infrastructure, a matter of logistics, and many challenges ahead for India.
I mean, that's what Abdul brought in very well. If you combine blockchain, trusted security with federated learning, amazing, right? Right now, one of the key challenges which you're facing is hundreds of millions of dollars of aid is, for example, reaching on the ground in India and other parts of the world, but they're not really reaching the right people. Unfortunately, there is corruption, there is nepotism, there is hoarding, which is going on. A really good blockchain secure system to track some of these, combine that with federated learning for actually doing research at the same time and leveraging the data to build up the models. I mean, that's the kind of solution which can save societies in real time. So what Abdul basically shared with us is something which I can very well see right now happening, or what Mikhail or Daniel shared with us. They have real implications in terms of making transition. And think about it even more deeply. Federated learning, with what Abdul, Daniel, and Mikhail have said in terms of getting blockchain, secure computing, and all. This is actually democratization of healthcare. You basically can have research being done in developed countries which have more resources to develop solutions, leveraging data from developing countries as well, to develop solutions which will actually save their lives and develop much more economical solution. This is the best aid which we can give. IMF, World Bank, UNICEF, aid, any organization you talk about, they want to serve people. This kind of technology can just transform it in a way that can basically grease the system and fill all the loopholes there. That's the way I'm looking at it.
Does anyone else want to jump in on this, or to add anything to anything that Tushar has said? Maybe Daniel, you can tell us. Yeah, go ahead.
Yeah, sure. Yeah, so I totally agree. The healthcare in general is a really interesting example of where we can, or where these technologies can make a difference. And I think we can think about it from many different levels, like from really high level collaboration to much more like smaller level collaboration, because the main problem here is also comes back to data access. I mean, we want access to more data. But in my experience, where we have also seen sort of the biggest or fastest progress is when you address maybe also smaller sort of use cases. Because you always have start small, like make successful demos or proof of concepts, like get those models into production and get them in use. So, and build on successes. And I think that like this concept of building on successes is what we have seen is also always what works best like across enterprises, that start small, be a champion in the company, be the one that succeeds with a project, and then continue on and move on. So one of the examples that we are involved with that's in pharma, but it's related. So that's also like, instead of trying to build like a big solution that solves everything for collaboration between pharma companies, it's very much focused on risk assessment, like or in silico risk assessment of new drug compounds, because there are publicly available data for risk assessment, but all major pharma companies, they have their own ways to do and big libraries of new compounds that they have risk profiles on. And these all differ between different companies, but like, what if they could also start to collaborate and build some models together? And what we have seen is the way to do this is maybe not like expect everyone to build one big federated learning model and then everyone should be using that, but like build it as an alternative. So here we're building a federated learning model. You can contribute, and then you can take this model and you have your own previous model, and then you can compare results and see, okay, so which one is better? And that way you gain trust in new technologies like this, because one of the problems here will always be that no one has full access to all the data that went into training these models. And trust.
No, go ahead.
The trust. I think that like it comes back to humans here. That trust is one of like the main characteristics we have to build in systems like this.
And Shterny, I will add something very powerful quote I heard from a friend. Pandemics do not know borders. Hence, the solutions should not also know borders. if it is going to impact people across the world, we'll come together to solve it. Daniel made a very good point. Pharma companies across the world started collaborating. People who were always at the throat of each other to make money, they're collaborating, right? So these kind of challenges, and federated learning is something which can enable this. When you face a global crisis, then we need to come back globally to fight against it. We have enough global talent to beat anything. We will beat it. Something like federated learning. So that particular quote, which I heard almost a year back, I think it was from Satya Nadella, the CEO of Microsoft, and their cloud computing and how they have been, it was used for pandemic related stuff, and they donated a lot of credits to people who are doing research. So very critical thing. So data, research, models, and it becomes much more. And the interesting thing is, federated learning is not expecting people to start trusting each other. Remember, it's not saying, hey, we are all going to become saint one day. We will assume that there will be people who may misuse data if we give it to them. There are people who may misuse information. What we are telling is, guys, even if your intentions are bad, we'll bring you together. It's like legal and law enforcement system in US and Europe does not assume that everybody is good. They say, dude, you can be bad if you want, but if you get caught, you'll be in trouble. And we will have police cars on the street to catch you. That's what federated learning is. There are bad people around the world who may want to get data from each other, misuse it. But federated learning, along with secure aggregation, differential privacy, secure computing, will make it so much that, guys, you come and do a fair play with us, or you don't play with us, but you can't basically do a foul play here. So that's the approach we have to take. And this event of hub security is very timely. I mean, we have shared this with a lot of people. A lot of people may not be able to join today, but they're certainly good. You guys are recording it. Hopefully you'll share it with people publicly. It's actually a service to humanity. This is not everybody even understands the power of federated learning or the power of secure computing and its impact on research and how it can change and transform lives, right? I think Shterny or Abdul, or Daniel probably mentioned about supply chains, right? Same point, right? Abdul made a very good point of models being there at different points in a supply chain, and then you capture those models. I mean, that can actually help us even figure out, detect, corruption. It can help us detect misuse of systems. And we basically, and it's not like all of those people have to be honest, but we'll have so many data points from which data will be collected, of course, in a secure way, but we can do certain kind of pattern recognition that we can easily figure out where things are not really going well. That can basically, address some of the key challenges. So I think everybody has made such a good point that, and hopefully, I'm pretty sure people at Hub Security are developing solutions which will hopefully take all of these into consideration. We'll love to hear actually from David as well about, the kind of solutions you all are developing from Hub Security perspective, which will take some of these concepts and develop products which we just now discussed can make a real impact on humanity. So Shterny, if you can help us hear a little bit more from David, that will be really nice.
Yeah,
I will. No, I appreciate that. I was letting you guys talk. You guys are experts on federated AI. We focus on it from security. It's funny, and we're looking at securing the whole area. And it's funny how you mentioned trust. I think Daniel mentioned trust. We're a paranoid security company. We look at zero trust. We don't trust anybody. And there's sabotage going on. So we're working on a pilot where the main goal is, it's actually not so much initially to look at the AI, but how do you secure the environment and how do you increase the data from multiple sources and safely do that without looking at that. And we do use something, an expanded definition of confidential computing, but the concept is we really want to secure it. And whether you're using federated or central AI, there's still an enormous number of people looking at sabotaging it. And there's multiple ways of sabotaging this stuff. And we look at, you've got to protect and secure even the local models and the local data, the transmission of the models. And if you're doing transmission data, transmitting it over, the central model, if there has to look at one, even very frequently, they don't even want the person centrally who's running this to be able to see any of the AI algorithms or touch it or see and touch any of the data is the things we're seeing. So even if you had the world cooperate on this, who's ever operating this has to be really cautious. And I'll take it smaller than a global scale. I'm assuming it may not start with 200 countries gathering together and sharing all their data. I'd be happy with, I've seen organizations individually, two departments won't share each other's information. So there's legal and political issues, but that's the idea, is building kind of, and then the data has to go back out, or the models have to go back out securely and run on each end securely. So there's a verification process, there's securely identifying them. We actually isolate the data on very secure enclaves, even when it's running. So if you happen to share data, whether you're sharing it, then not even the person running it can actually see it. But every step along that path, in our perspective, because we're looking at protecting it, and that's kind of the pilots that we're running, is to make sure we can increase the amount of data that's being used, but really look at it, how do you secure every single step that's happening along the way? Because guaranteed, there are people sabotaging it. You know, even the most useful things with sharing COVID information. And you might have seen even genetic information, people are sharing it, but I know there are countries stealing all the genetic information at the same time. So without getting into too much detail on our specific thing, there are multiple ways of confidential computing and multiple breadths and stuff of solutions. Tushar, you've mentioned some of those. And I think that's actually going to be critical. And that's why we're focusing on this with an extremely large company, on how to protect that entire path. And that was one of the things I liked about Federated. It does go a long way of keeping the privacy, but you still have issues of, I think, of stealing even the model passing back and forth, even on the endpoints. How do you even know who's coming in?
Yeah.
How do you know that the data in that endpoint isn't getting sabotaged, or the model at that endpoint isn't getting sabotaged? That's actually the stuff that we're dealing with pretty extensively right now.
Yeah, I think that's a great segue also to my next question, which is for Abdul. How can federated learning be applied to cybersecurity?
For sure, Shterny. So essentially, I'll mention a few use cases that federated learning could be applied to cybersecurity. So essentially, one of them is network intrusion detection for IoT devices. So that could be one of the use cases. So essentially, in that sort of setting, essentially, like, think of, let's say, like smart buildings, basically, which have IoT devices, and there are multiple sites that these IoT devices are on. So a typical setup would be that these IoT devices basically are connected to some sort of a cloud server through their local gateways. And in a central setting, again, the way the network intrusion detection would work for these IoT devices is that the network intrusion detection model would be trained basically on the cloud, and then the IoT devices basically can get the gateways can then get those models and then do an intrusion detection locally for these IoT devices. But as I mentioned before, these IoT devices essentially would be generating a lot of data and perhaps like uploading everything to the cloud, basically to train a model in the cloud might not be feasible, because it would be like too much, like the volume of data would be too big. Also, in safety critical use cases, it basically also introduces a latency where stuff basically has to be uploaded to the cloud. The model would then be applied to the data point, and then the result would be returned back. And that would introduce latency and might not be desired for your safety critical use case. So essentially, in a federated setting, the network, the gateways basically would be training models through a federation, and in collaboration with the help of, let's say, like a cloud server, which could be the parameter server. And at the end of this whole process, they would essentially have the model living locally on the gateways itself, and the gateways can then apply this model to the traffic that they are seeing from the IoT devices for network intrusion detection. The other example could essentially be basically like malware training classifiers for malware detection. And this basically, I think, aligns with what Tushar was trying to say in the medical health setup, where the companies don't want to share their private and sensitive information with each other, but they can still basically train models in collaboration without sharing any of their sensitive data. So in a malware detection case, the companies that are in this business, they would essentially have repositories of binaries, basically both malicious and benign binaries, which are business sensitive, and they wouldn't want to share those with each other, right? Because that is like asset, that whole binary repository is an asset to the companies. But so if they just train machine learning models on their binaries, then it means that they're just restricted to their data sets. But now in a federated learning, what it allows them to do is that they can train the models collaboratively in some sort of a consortium. They can use federated learning basically to train those models and get classifiers for detecting malware, which would be trained not just on their data, but also on the data basically of their peers, right? And that gives them that advantage that their models would have like much better predictive power. At TELUS, we are also looking into using federated learning for connected and autonomous vehicle security. So we are looking at both in-vehicle and inter-vehicle security. So essentially, we are looking at federated learning as an approach that can basically bring low latency to the table, and also with 5G, because everything is moving towards the edge, and you don't really want to basically be transferring stuff to the cloud. So this whole federated learning, along with fog and edge computing, basically, and the fact that IoT devices would be generating a lot of like a huge volume of data, like sort of like align very well together. So that's where we are looking into federated learning, basically for doing intrusion detection and misbehavior detection in vehicles.
No, what is interesting, Shterny, is Abdul really nicely aligned. So David basically talked about security to enable federated learning, and now Abdul said how federated learning can actually aid security. It's a very interesting way of how these two things have been brought together. I really loved this conversation.
Things aren't always so simple, but actually, hopefully, the group on here, the companies working on this, I think that's going to be a critical thing, actually.
Maybe I can hear
simplify it.
Daniel. What are some of the other main challenges that, when it comes to ensuring full privacy preservation in federated learning?
We mentioned quite a lot now, but or quite a few. But I think that the core concept here is that when we talk about federated learning and in the settings now that we mentioned where you're collaborating, I mean, what you basically do is you assume that you have some entity that you have to trust, basically, because you're sending your models to someone, and when you have a model, you can either go like you can backtrack or like do inference attacks, as we say, yes, to figure out what kind of data went into training this model. And also, when you have a model, you don't know where that model ends up. Someone could take it, they could maybe use it infinitely, and sort of that breaks the rules of this alliance where you work together. So this is where confidential computing comes in, because that's a way to add trust to this system. But what it depends on here, the solution that you might want to go for, I think depends on how critical is privacy of the data that came in. So because you can go the complete opposite way as well. So instead of having sort of full obfuscation, you could also go for full transparency, that everyone knows what happens and can keep full track of everything that happened when you're training a model. So this is one of the things where, for instance, a blockchain system can help. So that even if you don't share the specific data or the model that goes in, but you can like hash everything that happens. So it is possible to fully backtrack everything that happened in a system like this as a model is being trained, and being iterated to sort of develop the final model. And also, when you end up with the final model, how do you distribute this model, or how can you use this for inferencing? So this is also you can do. You could, for instance, encrypt this model, and you use like private and public encryption keys to sort of restrict access to this model, so that basically no one has unrestricted access to a model. But this is really like interesting area where I think that the complexity really grows with what is the use case that you're working with. And when you start from the most simple use cases, maybe security is not so important. So just as an example, the use cases that we see are most mature right now are use cases where you, for instance, a cross-silo use case where you in a company have one data center in Europe dealing with GDPR classified data or class data, and then you have another data center that has like all the data from the rest of the world, because it is like the overhead of dealing with the GDPR data is so much, so you don't want to do that with all data. But now you end up with like two systems that are basically fully identical. It's just that the data that you have in your databases are different. Then federated learning, it's quite easy to set up a federated learning system. You just have like two clients basically, and you want to combine these two models. And if you, the next step in a way where you also work with full trust in a company is, we talked about automotive here, but you can generalize that to, you can call it machine or system manufacturers, that one company produces a system. They have full control over the development process and also what kind of data is generated, how the data is stored, the full data pipeline. But in the end, it's a client or customer that owns the machine and owns the data that's generated on this machine. So this is also a situation where it's sort of it's easier to build up a collaboration system, even if this, and because you already have full control over the entire system. And then you go forward from that to these more like competitive cases where you can assume that there are sort of malicious actors in the system that might want to sabotage or at least gain unfair advantages.
Tushar, I wanted to very, very briefly give us a description of or a definition of confidential computing, and maybe a few ways, maybe a few examples of how it can increase the efficacy of federated learning just from a security perspective.
Absolutely, absolutely. So look at a microprocessor or a processor in cloud which does any kind of computation. And so when you are actually sending data to the cloud, there are three parts to it. There is data at rest, which means the customer or the consumer has data at their endpoint device. There is data which is basically in transit when you're taking it to the cloud, and then when you're processing it. The challenge was data at rest and data in transit, they were typically secured, but when you process the data, it was not secure. If there is a leakage there, data is lost, right? Secure computing at a high level is, hey, when you are processing the data on a processor, that also will make it secure for you. That's a fundamental concept. How you do it, there are multiple different techniques and there are multiple different players. Intel, AMD, ARM, they're all working upon it. Now, if you take it to the next level to understand how secure computing will work is, you basically have what are called trusted execution environment and security enclave. Consider it like a house where you have designated certain number of rooms where what is happening, nobody else can know until you have the permission to know. That's what is the next level in secure computing understanding. So you basically designate certain areas called trusted execution environment or security enclaves in a processor. Now, there is also a very interesting concept called homomorphic encryption, where you can send encrypted data to a processor. Typically, what you used to do is you will take the encrypted data, you decrypt it, process it, again encrypt it. Homomorphic encryption says you can process the encrypted data itself. That is where the concept of secure confidential computing comes in. Intel has done some good work using SGX, and Microsoft Azure is working on using it. AMD has done good work using some of the new processors which Google is planning to use it, and ARM is coming up with an architecture called Realm, which will be released soon, which is going to be kind of putting secure computing architectures or confidential computing architectures in their designs. Now, coming to federated learning, right? As David was pointing out, and I'll give you a very different analogy, and I'm going to pick it up from the country where hub security is. If you have to think about security of a country like Israel, how do you do it? Well, you have to think about the complete ecosystem of Israel in every point where security has to be. Airport, road, train, tram, bus, school, everything has to be secure, right? Similarly, if you look at federated computing, if you want it to work, you have to look at the whole ecosystem. all the way from where the data is to the model generation, model updates to, parameters being sifted or transported, models being learned. If you look at this whole system, if any point in security is weak, the weakest link defines the strength of the system. If you look at federated computing, one of the weak points can be when you get all these models from the individual endpoints to the centralized server and you're updating the model and developing a generalized or an average model. What if something gets leaked there or somebody basically breaks it? You're done, right? If we can secure that using confidential computing, that's going to be plugging in a very major hole. That's how everything fits. Happy to explain if I was a little faster. I typically like to make the concept simpler from technology perspective and then dive deeper into it so that people can understand. If I can understand it, anybody else can. That's how I think about it. So happy to get into specifics of it if you want, Shterny.
That was a good explanation.
Yeah, I wanted to ask David, maybe you can give us a follow-up on it because, right, confidential computing is talked a lot about as an alternative and is being complementary to federated AI. Maybe you could expand more on that.
You're
I will
talking
just
about
briefly, because actually I thought Tushar did a great job actually explaining the whole concept. And in its literal sense, it deals with protecting the data and actually the processing while it's running, right? Which is not so easy because you need it in the clear to run it effectively. And there's a whole range of stuff, and I'll just give, he mentioned Intel SGXs. They work on the actual core processor to protect it. And the one thing that I'll add to keep in mind from his explanation is there's a broader set around that has to occur. So Intel has the secure processor, but now you need to kind of build out a platform around that because that's just protecting the process, but you do have to then be able to secure both the data coming in, the applications. You have to give right from who has permission to what, make sure even the people running it can't see it, verify the information securely, protect the messages coming in that they haven't been sabotaged and looking at them. And so the only thing I'll say there is that's what some of the companies are working on. And that's, from our perspective, just for one plug, we kind of look at us as almost a secure data center in a box because we're putting all of those pieces together, the secure processing, but we're also doing like a secure firewall to check every message coming in and going out to make sure nobody's playing with this. Securing the data coming in, securing the transport of the data, encrypting the database, or even securing the data on the box. So when you hear confidential computing, there are multiple approaches. Homomorphic encryption, I said there's multiple ways of doing this. The trick is just when you look at it, look at the specific technique, and then you've got to look at the full solution, because at some point you've got to be able to simplify this for people and say, hey, run it here, and it's covering the entire range of stuff. So I'll just explain that as kind of a plug where Hub is heading. I thought the definition, Tushar did a superb job explaining confidential computing.
Makes sense. The only thing I'll add, Shterny, is a lot of times we get into this discussion about, hey, is confidential computing an alternative to federated learning, or is blockchain is alternative to it? Let us look at it as a holistic system. We need all of them to work together. Is it like asking in Israel, for example, I'm picking that example with the companies located there, as, hey, do we need a centralized security command and control system in Tel Aviv, or do we need like people on the forces in the ground in Jerusalem or Haifa? We need everything to work together, right? Similarly, federated learning is one part of the problem. Secure computing is solving it from a different angle, but all of this need to be coming together. Then only we can make a robust system. So it's not a question of if this or that. It's all about figuring out. And Abdul, for example, explained so well, right? Federated learning needs cybersecurity, and cybersecurity needs federated learning. It's like in cloud computing, virtualized machines need security, and virtualization itself brings concepts of security with it. So that's the way we have to look at it.
And that's why we brought it together, actually, the topics, because I do believe they're extremely complementary to each other from that perspective.
Makes sense.
And with that, we're going to segue into Q&A. We have about a half hour left to our event. So to anybody, any of our participants in the audience, if you have any questions, you'll see a Q&A button below. You can just drop them there. If you can't find it, put it in the chat. We'll see it anyways. But I wanted to start off with a question from one of our attendees, Atif. He asks if model verifiability is a challenge, then is it even possible to identify malicious clients that join the architecture to purposely sabotage the learning process? And anyone can just feel free to jump in. Mikhail, maybe you wanted to get on that?
So I guess I wanted to comment that seems to be related to this issue of Byzantine robustness, which I guess also is one type of security and federated learning, where the idea is that instead of, I mean, the most basic techniques, what they do is that instead of averaging the model parameters as an extension of federated averaging, they take some notions of high dimensional medians, so which is more robust to sort of noise, and then they could show that if some of the clients are sending basically some random noise instead of the true model parameters, so they could be robust to that. And I think Atif also asked another question, which I think is pretty connected to that. I think together they kind of form an interesting picture. Is the other question was how are poorly performing clients handled in the model convergence phase? So to handle the poorly performant clients, there is a different technique called distribution robust optimization, which says that instead of averaging the loss, instead of trying to minimize the average loss across clients, we try to minimize the worst loss of, across clients, like the worst convex combination of losses in clients. So this way we'll make sure that every client receives attention. But the cool part is that how do they interact? And I actually don't have a good answer for that, because if we try to give a lot of attention to clients which underperform, then how do we make sure that they're not simply, sending noise instead of the weights? So that actually, I haven't seen a good answer for that in the literature. Maybe just, maybe someone else knows. But
so I guess I can perhaps comment on. I think Mikhail brought up Byzantine robustness, and I think like some work that I've seen basically in the literature against these attackers that would try to sabotage the system by sending garbage updates is essentially looking at deviations from the mean as to like how much your gradient basically deviates from the mean. So the concept over here would be that perhaps like when the clients are sending updates, the normal ones would be closer to the mean, but if there's just sort of like random updates, and the attacker basically is trying to upload, let's say, like random garbage data, you'd just sort of see that it would be deviating quite a bit from the mean. So that's one approach that I've seen. Also, there could be like Sybil attacks basically on the system as well, where the attackers basically can have like multiple pseudonymous identities and sort of like try to throw the system off that way. So one attacker can basically like appear as multiple different identities within the system. So some works that I've seen over there basically is that those attackers would sort of like be very close together. So the normal updates basically would have like a bit more variation over there, but the attacker behavior would be very close, very close to each other. So all the attackers their updates would look very similar. So their systems basically like that would have this concept of adaptive learning, where they would essentially try to penalize the updates that are sort of like very close to each other. So I've seen that for Sybil attacks.
So I can add a little bit also. So what I've seen, so this problem is also a governance problem. Like who is invited from the beginning to participate in providing updates. So you can, if you have a very tight control and there are two participants in the system, like this problem becomes easier to solve. But if you have thousands of clients and someone gets access to one of these cars and start to manipulate the data, then like the problem could be much harder to solve. So that's just one approach into it, I think, as well. To think about the system that is around.
Yeah. Perhaps I can throw in like a couple more approaches. Like one approach could also be, I think, is that if your central parameter server basically has like, let's say, like a few samples like which are labeled then one approach could be that as the model updates are coming in, it can sort of like apply those local models basically to its own sample data to sort of see, okay, like how well is the detection going, right? So if the detection basically like looks off for, let's say, like some clients, then it can detect that, okay, like there's some sort of like attack going on from that perspective. But that depends on the fact that the central the parameter server would essentially have some label data samples for that problem that is that is being solved. The other approach I think like that I was bringing up was like this whole blockchain system, and that's where I think like it very nicely fits in, where like one blockchain basically eliminates the central point of failure, but more than that, by having this model in a marketplace where the buyers can come in and they can basically like buy those models and they can try out those models, like it basically like sets up this whole reputation system where those buyers can then give feedback as to how well the model is performing for them, and that way you can sort of penalize like the clients who have essentially participated in this whole training process, right? So I mean, it's not like an algorithmic solution to dynamically detect as the updates are coming in, but through this whole feedback loop, like through the blockchain, you can essentially like factor in like you can basically have a reputation system and penalize the clients or the attackers in the system.
Somebody is just asking here in the Q&A, how do you distinguish between a malicious user versus a user which has a benign deviation in the data distribution?
Yeah. So can I add, because I think this is really related, and I mean, you basically can't, or at least not in all cases. But what you can do is that you can have different approaches to validating the models that are created on each client. So like you can imagine one system where you just have, like Abdul was mentioning now, a central validation system. So all models go up to the aggregator. There is a test set at the aggregator, and then you check these models as they come in and see which ones sort of are accepted as potential updates and which are thrown away or rejected. But you can also have a system where in order to accept the model, the aggregator sends out the new potential global update to all participants. They all have private test data sets, and then you can have different approaches to sort of either you have a voting round where you need majority vote for a new global model to be accepted, or you might have like a strict requirement that everyone needs to accept this new model. Or you could even have like a system where you take the individual model updates like from each participant and distribute them out in the whole system, so that like each potential model update is checked or tested like on other participants with their private test data set. So like there are many different ways to do this, but this is all up, like I think, to the use case, like who is participating, what kind of data, and what kind of clients are there here, and then have a system that makes sense in this setting.
Can you actually tell? Sorry if I'm asking. Can you actually tell if it's malicious or benign? You really just know if there is.
Yeah, I would say no. Like, I mean, in some cases, yes, but does it matter? I don't. If it's like a faulty sensor or if it's malicious, it's the same thing. Like it's crap data in. So I think it should be handled the same way, because it's not improving the model for everyone else. Like, or everyone else is not benefiting from this.
Right.
From this.
I guess it depends on the scope of the maliciousness.
Right.
What if a client which is a business and not a sensor? Like, so here there is sort of the robustness and the fairness seem to be kind of contradicting each other, because robustness says, we should discard those with that deviate from the majority distribution. But fairness says we should be sort of mindful of those that have like different distributions, even though they're underrepresented in the data. So I think seems to be not an easy trade-off to solve. So I think just, I mean, of course, if it's sensors and so on, maybe in some cases discarding them is fine if their distribution is so weird. But I think there are a lot of contexts where, what if it's a data from some like small hospital that, doesn't have a lot of resources and so on, versus like data from others is some more developed hospitals with better medical equipment. So the types of data could be very different, and the data from the little hospital in a rural area could almost look like noise. unless we like consider it more carefully.
Yeah, and
Right.
just an addition that many times, like these small, also maybe where the data distribution is different, and maybe where you have more of underrepresented data is really valuable. So you might not want to throw it away. You even want to maybe amplify some of this data.
And they're going to do so, but the problem is that they contradict the ways of defending ourselves from the malicious side. It seems like one or the other in a sense.
Makes sense.
In on this?
Yeah, I had an interesting different angle to it, and Daniel, Mikhail, Abdul, feel free to correct me or get me a better thought process. There is a problem of malicious user, and then there is this concept of model drift, because the data which is coming from users is not exactly the way we thought about it, right? And these two can be different, correct? Because if there is a model drift, we'll see it across many users. The malicious one, it's unless users are doing it in a coordinated way, we probably will see malicious users in one or two different points. And those two cases have to be differentiated. And in case of model drift, we'll have to figure out how to retrain the model parameters to cater to it. So what I'm trying to get to it is some of these cases of not seeing data which is expected can probably be classified into two areas of malicious versus model drift and accordingly tackled. Daniel, I would love to hear your thoughts on that.
Yeah, I totally agree with this. But I also think it's maybe a problem with not many obvious solutions right now.
Got it.
Yeah.
Got it.
Maybe
Yeah,
one
Mikhail,
way to balance the two is that I think personalization could be useful here. So we could, when learning the global model, we could try to be robust and learn actually some good feature representations, right? Which are kind of truly useful for a task. So we know, let's say for image, for text data, the feature representation, the transfer across tasks. And then through the personalization, even the clients which have sort of different data distributions, maybe they have very different image distributions, they could still benefit from good features that are learned globally. So I think maybe through personalization, it's possible to try to do both.
Makes sense. Makes sense. I wanted to just put it out there. Go ahead.
One of our attendees is asking if model verifiability is a challenge, then is it even possible to identify malicious clients? I'm not sure if we answered this already. Instead of just filtering out the bad.
I will tackle it in a different way, right? They're saying if model verifiability is a challenge, then can we even do something like this? I mean, this is almost like, if there are a few corrupt cops in the country, do we even the police system is needed? It's something like that. Look, it's not like every model cannot be verified or every model is deviating. We understand it may not be a perfect system, and you start it from whatever you have. It's not a perfect system, 100% foolproof system. The whole goal of artificial intelligence, I think, which Abdul was also highlighting, is through a process of iteration, you basically weed out the corrupt or weed out the problems or the challenges. So even if the model cannot be completely verified, but over a period of time, as it goes through iteration, it goes through data, and you have model aggregation happening over a period of time, it will minimize the impact of lack of ability to completely verify the model. But does that mean we should not have it in first place? It's not the right approach. That is with any kind of system. And I'm trying to broaden the thinking. Like, we cannot be like if vaccines, for example, are not basic, we can't verify 100% if after taking vaccine, you will not get COVID. It's still less than 100%. Does it mean vaccines should not be taken? They need to be taken, but over a period of time, we can probably improve vaccines based upon new data that we get. That's a little bit of an approach that you have to take. Same thing with security. Is secure confidential computing or secure computing completely eliminate the problem of malicious users getting into the system? Probably not, but you start with where you have. The only advantage is any kind of artificial intelligence system is a self-learning system, because of which it improves itself over a period of time and hopefully catches things. So I think that's the way we'll have to look at it.
Somebody is asking here, so if the number of users is large, then the attack from the bad actors, I'm not sure that they would be able to influence the model at such a high degree.
They can. Just think about when you compute a mean of points. So I can change the mean of a lot of points arbitrarily by picking one point adversarially. So, and
I mean, is the person referring to something like a DDoS attack, like distributed denial of service attack kind of a thing. A number of malicious users work in a coordinated manner. I mean, that is a very different kind of a problem we will have to tackle and see. And some of the traditional security concepts related to denial of distributed denial of service attack will have to be brought in and combined with federated learning. David, it seems you want to say something as you have been nodding the head.
No, I'm nodding. One, because I'm agreeing a lot. Two, I think what I really agree with is it's a matter of you could dramatically reduce the amount of malicious attacks and those kinds of things. There's no such thing that 100%. But I think the impact is how to dramatically reduce it, and by securing and by having things in there that secure denial of service attacks, breaches, sending in poor data, whatever. I think there are seriously good ways of actually dramatically reducing that. But I agree, there's nothing I know of in security. No one would ever claim that something's 100% secure.
Yeah, one good thing about security is like police force. The very fact that when people know there is security, it deters a lot of people. Of course, there are some people who are so motivated they'll come and destroy you, but it certainly deters people. And and once you know that you can be caught at some point of time, people think twice before doing it.
Yeah, but there are different kinds of groups attacking. There's the individuals being malicious. There's the nation states with phenomenal resources to go and do these. And it's not just healthcare. Healthcare, yes, has some obviously major privacy issues instead of financial. But there are also things working on drones, managing farms and stuff where privacy might not be an issue, but protection is certainly an issue of securing it. Military applications all over the place where, again, privacy is not always the issue, from there. But it's the level of resources and the cost you put against it. And for the individual, we could probably get pretty close to securing it. For the nation states, that takes a whole nother level of security.
Right. We have around about under 10 minutes left, and we have questions pouring in, right? From our.
We're actually 20 minutes over, but that's good.
Yeah, we're 20 minutes over, but we extended, so we have under 10 minutes.
We have 3 days left.
I know, Mikhail, you wanted to ask a question to David. I have a few quick, small questions I'm going to shoot at you guys. Maybe we can give 60-second responses, try to get through them. We have an anonymous attendee asking, can federated learning be used with unsupervised learning?
So I can perhaps take that one. So one way of doing unsupervised learning basically is through auto-encoder decoder methods as well. So which is basically like a deep neural network way of doing let's say like unsupervised learning. So if we go with that, then definitely it's again your neural network, and you can use federated averaging to basically like train such models. I haven't seen like federated averaging, like federated learning for clustering as of yet, but I'm pretty sure that even that can be done. Let's say like k-means or other clustering approaches perhaps could be done through federated learning as well.
The model fusion techniques we could do it with mixture models, which is k-means, hidden Markov models, topic models, and in those cases it's actually provably really good with just a single communication round. You don't need to exchange data back and forth or like weights or anything back and forth. Just one communication is enough.
Okay, are there, another question from our audience, are there any algorithms that allow matching parts of multiple neural networks so that an aligned averaging can take place rather than naively averaging the parameters?
Yeah, just again, it's what I mentioned earlier about model fusion. So the way we decide what to average is by looking at certain types of similarities between as a neural network weights, so rather than just average and element wise.
All right, we have another question here. Can we quantify the trade-off of robustness versus fairness as alluded by Mikhail earlier?
Well, you could. If you make assumptions on how much your distributions of struggling clients are allowed to differ versus by how much noise is your malicious clients are going to stand. So there are ways to maybe deal with it. So you can say like, well, if the malicious clients, because if the amount of data deviation or distribution deviation that struggling clients will have is not too big, then you could kind of bound your robustness by that. So you can say like, I'll be robust at least to this much noise. So maybe some of those clients will be sending little noise. Some of them will truly have just a different data distribution. But there could be some theoretical bounds of that sort.
Mikhail, I know you had a question for David.
Yeah, so I just, I guess, wanted to summarize, I guess, the type of threat models. So because I was personally a little like lost with, all the security, like there are all different types of problems. So I guess there are like the threat models that I've seen people look at the like AI or ML literature is usually like there is either robustness at deployment, which is adversarial robustness. There is robustness versus, this malicious client that sends noise, which we already discussed. Then there is robustness against, clients or server trying to infer the data distribution of each other. So that's something that we usually try to address with differential privacy. And there is also things like a backdoor attacks to, that like you try to inject some kind of malicious model behavior. So do this there are methods for addressing all of that. So I'm wondering, is there some types of threats that you think are relevant that you don't find the current state of the art to be good?
So first of all, the things about protecting even the model and the data, when Tushar was talking about confidential computing and protecting it, like even while it's operating, that field is relatively very, very new, and these are evolving now. The solutions for that is just coming out. Even things where he's talking about, just give you an example, homomorphic encryption, they're still research stage in one sense. There's still a lot of performance issues that you have to resolve. It's limited in how much data you could actually use, and there's certain other limitations in it. So from one sense, parts of it is, and I'll answer that in two pieces. There's two parts. Security is like a lot of different pieces kind of patched together to try to cover things, and people find gaps of it. The thing that I feel needs to happen going forward is, one, it kind of needs to be pre-integrated in one place. So you have somebody who's actually protecting denial of service attacks and messages and people getting at the algorithm and manipulating that in one environment. So all those things are actually handled in one place. So it's a combination of A, putting existing stuff together, and B, there are definitely innovations as far as things with confidential computing, and it's why there's several different approaches, because they're at various stages of executing. Even things we have in there that deal with hardware and firmware-based firewalls that were patented, that we've built completely new to handle this kind of messaging coming in, checking, and going out. So there are definitely innovations to help solve some of these things that are going on. And we look at it as two things. One, it's got to be comprehensive because it's very difficult for people to piece this together. And two, there are some new innovative stuff that actually is coming on there, dealing with like confidential and certain kinds of firewall stuff as well. By the way, just as a plug, for those who are looking at, for blockchain for auditing, we actually started there. This platform is actually a secure means of protecting things going on the blockchain as well. So we actually cover that piece. To the point that if anybody stole anything off this box in crypto, they can get insurance up to $400 million for being able to steal a Bitcoin off the box, for example, or any token. So I would answer that in two pieces without diving down into too much in each part. There is stuff of just putting it together in one place, and there is stuff of there are some definitely new innovative approaches that are stopping each one of those things.
Sure.
Yeah,
Shterny, I would like to advise, or in a way say, or the audience to think it this way. Okay, today's webinar, amazing work by Hub Security, has given you ideas about fundamental concept of federated learning, blockchain, confidential computing, and all. Please do not think like, hey, where can I apply federated learning? Where can I apply secure computing? Do not do not take a hammer in a hand and look for a nail. Step back and think at whatever problem you are working with. Think about the challenges. Keep this concept at the back of your mind, and then slowly try to figure it out. And then you will see that some of these will fit into a problem, some of them may not. And sometimes even when you put all of these frameworks together, still it will not solve the problem, and you may need something else. And that's where we will be coming to your help, because Hub Security will be sharing our contact information. In my case, it will be my LinkedIn profile with all of you. So if you want to reach out after this event, say, hey, Tushar, I have this kind of a problem and I'm thinking about these different things to apply, what may be missing. But that's the key message we want you to take it from. So do not just get excited about federated learning as a panacea for all challenges. It's a new paradigm, which is kind of a very powerful force to attack the problem and solve it from a lot of different angles. But that's something I want the audience to take it, and that will really help. That will really help.
Thank you. In Hebrew, we call it a fergun. So thank you for that. Well, I wanted to wrap up in a minute, but does anyone else on our panel have anything else to add?
That's a dangerous question. I have a feeling we could go on for days, but okay.
All right. Well, I think we had a really great discussion here. And just so everybody knows, this event was recorded. It's going to be up on Hub Security's YouTube channel, so you can check it out and share it with all your friends and family. And also, I want to just say a big thank you to every one of our panelists for joining us: David, Abdul, Mikhail, Daniel, Tushar. I really appreciate it, and I think this was a really great discussion. And I hope to have many more like these in the future. If anyone from our audience would like to get in touch with today's panelists, you can feel free to reach out to them directly. All of today's attendees also will be receiving an email in the coming days with contact information. So don't be afraid to drop our panelists a line, and if you have any other questions, feel free to reach out to them. And to stay up to date on upcoming webinars, follow Hub Security on LinkedIn and Twitter, do a short promo. And you can also follow our weekly digest on Medium, written by me every week, and top stories coming out of the cyber and security sphere. And with that, I think we're going to end here. Thank you guys so much again for joining, and thank you to our wonderful panelists.
Thank you, everybody. This was one of the most interesting panels I've attended. Thank you.
Thank you.
Thank you.
Thank you,
everybody.
It was a great time. Thank you.
Thank you.
Bye.
Thank you.